Okay, today we're going to do a somewhat fun activity regarding Snell's Law. So it's more of a mathematical history than anything else today, but let's review what Snell's Law is. What do we use Snell's Law for in physics?
Calculating the angles of light bending to different things.
Right, calculating how light is going to move, what direction it's going to travel when it goes from material A into material B. And so here we have two pictures, light coming from material A, which is air, into material B, which is blue, water probably, and it bends toward the normal because it's going into something with a slower speed. If it were to go the reverse, going from water into air, it goes away from the normal because it's going to something with a higher speed. And we've learned the equation that deals with this Snell's Law, which I know this font here is horrible. I copied the whole picture, including Snell's Law, that says index refraction of medium 1 times sine of the angle between the normal to the surface and the incident beam, medium 1, is equal to index refraction 2 sine of the angle between the normal and the refracted ray. So where does this come from? There's a couple ways to derive it, and we're going to look at one of the ways, which is, I think, the most interesting way. So first, some history. Brachistochrone, which I mispronounce half the time, is a word that means shortest time. Brachisto, shortest. Chronos, time. And in 1696, Johann Bernoulli challenged the world to a math problem. You know, it's kind of like, I don't know, almost like you have people that will ask questions in court and people are rushing to try to answer it type of thing. So he published this in a journal. Who can solve this? And the problem was, notice there's something that Galileo had considered in 1638, but he couldn't solve. What's the difference in 1638 and 1696?
1696 is later.
Ooh, man, that's an astute character right there. The difference is Newton had invented, okay, I say Newton. Bernoulli would have said Leibniz invented calculus in the intervening period. And calculus is a method where you can find how to minimize or maximize something. Right? You take the derivative with respect to the variable you want to minimize for, and you set it equal to 0, and you're going to get the values of that variable are going to be maxima or minima. And so with that then, Johann Bernoulli challenged mathematicians to solve what path provides the shortest time to go from point A to point B with only gravity acting on the object. So just as an example, say we have a ball that starts here and it's going to end here. What path is going to take the shortest time to get there? Now let's get out of the way the stupidly wrong answers. Whoops.
No, that was wrong.
Yeah, that would take a really long time if it takes that path, right? It's annoyingly long compared to the straight line, and it's going up, which means the speed's going to drop. It's probably not going to do that spontaneously. So that's an annoyingly wrong solution. What would be the naive, like if you asked a second grader, what would they put for the solution?
I haven't been that age in a while.
Yeah. A second grader knows the shortest distance between 2 points is a straight line. Otherwise known as a B line because we're going from A to B. Yeah. And so that might be an answer that a second grader would give. It also might be an answer that somebody that's a freshman in college would give. Because you tend to think, okay, it's going downhill. It's the shortest path. That should be fast. But somebody who's a little more astute is going to say, well, that's not the fastest. What would make it go faster? Excuse me. What would make it take less time? Well, gravity is what's making it move. But what path would make it take less time?
Steeper.
Okay, if it's steeper, because if it's steeper, it's going to go faster, right? And so if we do something like, let's say this, that is going to go faster initially, and then it's going to carry that speed throughout, so it should go quicker. But if I go like this, well, and that's supposed to be a horizontal line at the bottom. That's got the fastest speed, but it's going too long of a distance, and it's still going to take longer than the shortest path. So the answer has to be somewhere in between paths 1 and 3. And how we find it? Well, then we have to use variational calculus. And of course, Johann Bernoulli had already figured this out before he published it. You don't put out a challenge and then say, oh, golly, you're right. You're like, well, I have the solution and you missed it. Solutions were provided by a number of famous characters. Sir Isaac Newton, who those of us in the English-speaking world credit for inventing calculus. Johann Bernoulli's brother Jacob. I put the full names here because I like them. Gottfried Wilhelm von Leibniz. He's the other person that gets credit. He's the person that the Bernoulli brothers would have said invented calculus. We are Francois Antoine Marquis de L'Hopital. You guys have all learned L'Hopital's rule, right? These are all people who submitted answers. Now, Isaac Newton, he got the magazine, stayed up all night, sent his solution in the next morning, along with a note saying that he does not appreciate being pestered by foreigners about mathematical things. He knew that he had to answer it, or they were going to say, oh, you don't know math. You think you invented it, and you can't even do it. But at the same time, he didn't appreciate it. So they all came up with an answer, and the correct answer is a cycloid. We're not going to go through the math of that correct answer, okay? It's not a simple problem. It's not one that we can do. It can be done, though. So this is saying, going from A to B, the shortest path would be D there, which is pretty similar to what I drew in my picture. But mine was freehand, so it's certainly not the right one. So that was the solution. Now, the story is, I think, a little bit interesting just about, these people who we consider, the huge brains behind calculus. I mean, when you study calculus, you learn about L'Hopital's rule, right? And you learn that Newton invented it, or you might learn that Leibniz invented it. Anybody, I think I talked about this before, obviously not to Ariane. Why is there controversy about who invented calculus?
Because Isaac did it first, but Leibniz actually made it incorrect, technically.
Well, Isaac Newton, during the Black Plague, when he had nothing to do with this time, he was studying things like what happens when an apple falls from a tree, and he came up with his 3 laws of motion, and in trying to work with those, he realized that there was no math that would allow him to solve the problems he wanted to solve. And so he invented what he called this mathematics of fluxions, and used that to solve things, like the orbits and stuff like that. But he didn't publish it. He just said, I come up with this new math of fluxions that allows me to do this. And so as I understand the history, Leibniz came over and said, hey, can you explain this to me? And so he did. And then Leibniz published about it. And so I think there's no controversy. Leibniz is the first person who published about calculus. But then the controversy is, so did Isaac Newton invent it? Or did Leibniz, since Leibniz is the first one to publish? In most cases, the first one to publish is the one that gets credit. And so that's really why there's controversy here. And I've never read anything by Leibniz or Newton. I know there's Principia Mathematica that we all should probably read, but I'm also told that it's horribly hard for anyone to understand, including people who are really gifted in math. Leibniz is the one who came up with the terminology and the symbols that we use in calculus. And so there is a very strong Leibniz influence to the calculus, so there are not very much Newton influence. Okay, so why was this important? It's important because based on the discussion that followed after this challenge by Johann Bernoulli, Euler in 1744, or excuse me, it's actually 1744. You might, let's back up. Yeah, this was 1696, right? Yeah, 1696. So Euler in 1744, he published a method for solving physics problems using the same variational principles. And then Lagrange, and I should have put Euler and Lagrange's full names because I don't know them. Lagrange in 1760 polished it up into what we now call Lagrangian mechanics. And so if you're a physics major, you'll take a dynamics course in which you will learn Lagrangian mechanics. And you make this thing we call the Lagrangian. So L here is the Lagrangian. It's a function of Q, Q dot, and T. So first of all, what is Q? Q is a generalized coordinate. And you should be saying, generalized coordinate, what? What does that mean? Q could be X, Y, Z, or it could be theta. Now, theta doesn't have units of distance, right? So there's no unit requirement, but it's some coordinate that tells you about position. And notice it's a vector, so you have the directionality. So X, Y, Z would be our vector. Q dot, what does the dot mean? It means the time derivative. So this is, putting it for the simplest problem, L is a function of X, X dot, or V, and time. And that's constructed by finding that kinetic energy is a function of those variables. So for something that's just translating, kinetic energy is 1/2 mv squared, so it only depends on the Q dot. And then the potential energy, if it's gravity, it's just mgh, so it only depends on the Q, right? So you make this function, and your choice of variables are what's listed there. And then, using the variational principle, you take the partial derivative. Now, I know 3 of you are studying partial derivatives right now, but we've talked about them all year. The partial derivative is the easy derivative. A partial derivative, I'm saying this for Ariane, you haven't studied partial derivatives, right? He's in Calculus 1.
Yeah, I haven't done that.
Yeah. So a partial derivative is a normal derivative except for anything that's not this is considered constant. So this is a function of, Q 1, 2, 3, 4, 5, Q dots of 1, 2, 3, 4, 5 and time. And you take the derivative just with respect to one of them and treat all the others as constant. That's what that means. So it's the easiest derivative you can take because you don't have to worry about, you don't have to worry about certain chain rule things, And then you take the time derivative of the derivative with respect to the Q dot with the same, so if this was with respect to X, then this is going to be with respect to X dot or V in the X direction. And that's equal to 0. It turns out this is a really easy way to solve really complex problems. So when I was taking that class, I was like, wow, all the things I did in general physics that were hard in mechanics, now it's easy using Lagrangian mechanics. So it is very important for our building up the physics that we do today. Now, for Maz Principle, once again, notice the date. Fermat said this before Bernoulli's challenge. He said that light will take, I've got it. I've already got it in red. Now I'm going to highlight it, which is going to make it look, whoops, that's not that. There. Which is going to make it look like it's in black. First, I may not ever erase it. Okay, did make it look like. Light takes the path of shortest time to get from point A to point B. That's what Fermat said. Now, why did he say that? He said it because if you look at Huygens' principle, which says that each point on a wavefront can be treated as a source of new light, and light goes out, it comes from that. But after this development of variational physics, we can solve this. This is the easiest variational physics problem I'll ever see, thankfully. And so we're going to do that. We are going to show that if we apply Fermat's principle, that we derive Snell's law. So here is the last slide of the presentation. Here is the diagram for what we're going to do. And I have two pictures. One with a picture of a lifeguard going to rescue somebody at the beach. Those who know me know I love the beach. And if you have somebody out there that's drowning, if the lifeguard takes that cyan path, it's going to take them longer to get to the person because they run a lot faster in the sand than they can swim in the water. And so the fastest path is going to go a little longer in the sand where you run fast and a little shorter in the water where you swim more slowly. So we want to do the same thing with light. So we're going to work exclusively with this picture on the right-hand side. And let me add a few things to this. I still have it on the highlighter. L1 is the length from P to A. Nathan?
This is only in the case of refraction?
Refraction, yeah.
Yeah.
I say refraction because you're going to learn about diffraction in lab today. So L1 is this length going from P to A. How can I find L1 based on the sides of this triangle? Based on the sides there of the triangle, what is L1? That would be cotangent theta 1 is what that would be. But I want to find L1, this length. Use the man, English is failing me today. I will use the Pythagorean theorem, square root of x squared plus a squared. Now, in the problem, in the setup, it's a distance d parallel to the interface going between P and P prime. So this distance from here to here is d. And it's a distance A normal to the interface from P to the interface, and a distance B normal to the interface from the interface to P prime. So we have those as fixed parameters of where P and P prime are. So A, D, and B are all constants. But X is the point where you go from one material to another. That's the variable. And we are going to minimize the time it takes to go from P to P prime by varying X. So we're going to vary between, for instance, you could conceivably come out to here and then go that way, clearly losing, but it would be a path. And we're going to take derivative with respect to X, set that derivative equal to 0, and find the value of X that makes it the fastest. So I found L1. What about L2 down here? This is L2. What's L2 equal to? Yeah. D minus X quantity squared plus B squared. Right, Pythagorean's theorem again. Now, why did I find those? Because the time depends on the distance and the speed. So we want to find the total time. So time is equal to time 1 plus time 2, where time 1 is the time in medium 1, time 2 is the time in medium 2. And then I need to find what those are. So we know by definition V is delta X over delta T, right? That's the definition. So if I want to find for delta T, that's delta X over V. That's all fine and good, but I want to introduce one more thing. Speed. We've talked about the index of refraction. How does index of refraction relate to speed? That's nice. Okay. Speed, the way Nathan said it is correct. The index of refraction is the speed of light over the speed in the medium. I actually put the speed in the medium is speed of light over n because I want to solve for V, for V, and wasn't listening carefully when he said it correctly for the question I'd asked. So I'm going to put that into my equations for time. So I'm going to have time 1 is equal to distance 1 over speed 1 is equal to distance 1 n1 over the speed of light. And similarly, time 2 is equal to length 2 over speed of light 2 is equal to length 2 n2 over c. So there's time 1, there's time 2. L1 and L2 are both functions of x, the position where I enter or go from medium 1 to medium 2. So I'm going to write my full equation then. Time is equal to L1 n1 over c plus L2 n2 over c equals 1 over c times L1 n1 plus L2 n2. Now L1 and L2 are both functions of x. But to save us some time and annoyance, okay, so I was working with Nathan on one of his calculus problems yesterday, and you guys had to, what was it? Take the derivative of something that was the square root of this squared plus this squared plus this squared or something like that. Yeah. It was really long. Do you guys remember that problem? This can be that way too, but we're going to simplify it by keeping L1 and L2 as functions of x. So now for minimizing, going to our calculus. If I want to minimize something, what do I do? By varying x. What do I do?
You change it. Isn't n the speed?
Well, the ends are fixed. The only thing that's a variable is x in my equation, right? Since L1 and L2 are functions of x, everything else is fixed. But in general calculus terms, how do I find the minimum value for t? Minimize any function in calculus. What do you do?
Partially.
You do what?
Partially.
Not partial, but the exact derivative. So I take the derivative of my variable I want to minimize t, in this case, with respect to the variable that I can vary, x, and set it equal to 0. Right, because you have your time is a function of x. If it goes like this, it has a slope of 0 at the top. If it goes like this, it has a slope of 0 at the bottom. And so you're either going to have a maximum if it's like this or a minimum if it's like this. But in both cases, the slope was 0. So mathematically, that means I'm going to say dt dx evaluated at x min equals 0. Evaluate x min means I'm putting in whatever x gives me the minimum. So now let's do our work. So I have 1 over c, that's a constant. N1 is a constant. But L1 depends on x, right? So I'm going to have dL1 dx. And likewise, N2 dL2 dx. So now I just have to find those two derivatives, dL1 dx and dL2 dx. So L1 square root of x squared plus a squared. So dL1 dx is equal to, I take derivatives of a square root. Ariane, how do you take derivatives of a square root?
You
into, like, yeah.
So derivative of u to the 1/2 is going to be
Negative? No. 1/2 times u to the power of 9.
right 1/2 times u to the power of minus 1/2, or 1/2 square root of u. My square root of u here was L1, so it's 1/2 L1. But then my u was a function of x, so I have to use the chain rule. And so then on top, I'm going to multiply by the derivative of u, the derivative of x squared plus a squared. Well, what's the derivative of x squared plus a squared with respect to x?
2x.
2x. So my derivative of L1 with respect to x is x over L1. Once again, I'm using L1 because it's easier to write than square root of a squared plus x squared. But also because if I look at my picture here, my diagram, what is x over L1? This goes in the direction that Trace was thinking earlier.
Based on the hypothesis.
It's the opposite over hypotenuse.
Yeah, opposite side, and upside down.
This is the angle, x is the opposite. So opposite over hypotenuse, which trig function is that? Sine theta 1. So I come down here. Now we have to do the same for L2. So if I do dL2, I've kind of run out of space. Dx, that's going to again have the 1/2 and then L2 on the bottom. And then I have the derivative of the inside. Derivative of the inside is going to be 2d minus x. But then I have to do the chain rule once again because it was u squared, right? D minus x u squared, the derivative is 2u du. And so then I have the derivative of the inside, which is minus 1. Well, my 2's cancel. Dx over L2. If we look at our picture, or d minus x is this distance here. L2 is the hypotenuse. So what is d minus x over L2? Sine theta 2. But we can't forget the minus sign. So this is equal to minus sine theta 2. So plus n2 times minus sine theta 2. So this thing equals 0. First thing we should do is multiply both sides by c. That gets rid of the c on the left side, and 0 times c is, surprisingly enough, still 0. And so, because I've run out of space, I'm just going to, if we multiply both sides by c, and then we move this to the other side of the equal sign, we have n1 sine theta 1 equals n2 sine theta 2.
And that's how we came up with the equation.
That's not the original derivation. The original derivation is from Huygens principle as we did in class a month ago or whatever. But this is another derivation using a Brachistochrone problem. Not the, but a Brachistochrone problem. Find the path of smallest time. Nathan.
Could you explain again how L1 turned into dl1 over dx?
How 1 turned
Like
into?
when you derived you took the derivative of t. So go back.
Okay.
We took the derivative of t.
Yes.
L1 n1 turned into n1 dl1 over dx.
Okay, so I was taking the derivative. So here's my t equation right here, right? And so 1 over c is constant, so that stayed out front. n1 is constant, so I just put the n before the derivative. And so since I'm doing d dx, since L is not constant, that leaves here dl1 dx.
Okay.
And likewise for the second term, dl2 dx, the n2 is constant.
And then can you explain again what you did after that?
So after that, I went and I calculated what the derivative of L1 is. So here's L1. Calculated what its derivative with respect to x was, which is this right here. And then likewise for L2, which is this right here. And then I substituted those in. So this here was the derivative of L1 with respect to x, and the thing in the parentheses is derivative of L2 with respect to x. That's all I have for you today. I know, Trace is sad.
I don't believe it.
Would you like me to do something else, Trace?
No.
No.
I just don't believe it.
Just in shock. Any questions about how this works?
I have a question about how it looks like. I mean, I know that we obviously just trying to get to the other one. But, I mean, what's the point? Like, what was the point of this?
Okay, what's the point of this?
I mean,
The point of this is, well, number one, because I find it very interesting.
I mean, like,
Number
why,
two,
maybe I
okay.
can define my question. Like, why did we need to know that Snell's Law is a derivative of?
of a Brachistochrone,
Yeah.
it shows us a new kind of physics problem that we can do, right? And the fact that it leads to that Lagrangian method, right? So this, right, the Huygens principle proof that we did in general physics class is an ironclad proof, right? So this is not necessary to believe Snell's law, but it does show that Fermat was correct in his statement that it takes the path of least time mathematically. So really what we did is we proved Fermat correct rather than truly deriving Snell's law. And so, you know, the value is in seeing how the physics can be done in a different way and how this then leads us to other things that are much more sophisticated and beyond the scope of this class. Any other questions?
It's not related to this, it's about a homework problem.
Okay, sure. What is the problem, sir?
That was last night's homework, the first one. You didn't watch that.
Uh-oh. Last night's is in the one that had to be turned in last night?
I already finished it up. I'm just saying to figure out.
Okay, so let me just
I had to do like part one.
go to the homework and take me a minute here. Oh, come on. You're supposed to remember me and let me in. Like I'm going to remember my passwords. Okay. In a second. So the first one you said?
Yes.
Okay, so we have a myopic person has a prescription for glasses which have this power. What is the far point in centimeter? Nathan mocked that last night. If her glasses are 1.75 centimeters from her eyes. Really funny thing, I think. Some old school physicians pronounce it sonometers. OBGYNs will say, she's dilated 7 centimeters. Don't ask me why. So we have some important numbers here. We have, let's see if I can. Copy that. I've had some success with this. I said in the class, let's see if I can do this. And a student said, well, how are we expected to do it if you're not sure if you can do it? My answer was, well, I'm using a Surface Pro trying to copy and paste. Okay, so here we have it. Person with prescription glasses of minus 0.55 diopters. So we have power. What does a diopter mean? Y'all did this last night. 1 over meters. So that's the power of her lens, which is 1 over the focal length. That's just where I was going. So they basically told us the focal length. When you know the power of your eyeglasses, you know the focal length of your eyeglass lens. Show answer, no attempt. What is her far point in centimeter if her glasses are 1.75 centimeters from her eyes? So we have to start with far point. Ideally, how far away can you focus? So far point ideal is infinity. Now, if somebody has a far point that's not infinity, then we call them myopic or nearsighted. And they're going to wear a glass that makes it so if the object is infinitely far away, the image is at their near point. What kind of image is it going to create? A real or a virtual image? Virtual, because it's on the same side of the lens as the object. So eyeglasses will take an object at infinity and create an image, a virtual image, at the actual far point. So now I draw my picture. Here's the physicist version of the eyeball. Here is her lens. Remember we talked about in class, it's going to be a concave meniscus lens to correct. And we're given that that lens is 1.5 centimeters, I believe, from the eyeball.
I think it's 1.75.
1.7. Yes, you're right, 1.75. Make it bigger so I can fit the 1.75 in there. And then we have the object at infinity. So my object is going to be out here. Little break. Distance object equals infinity. And then I'm going to have the image. Here's our distance image. So we all down with the picture? So now we just take our thin lens equation that says power is equal to 1 over f. It's equal to 1 over distance object plus 1 over distance image. And I solve it for distance image. So, inverse meters there for my units. 1 over infinity is 0. So that gives me distance image is equal to 1 over minus 0.55 inverse meters. And so I just have to take a calculator, take the most complicated calculator I can find. It is a CVS. It won't turn on. It's because it's solar powered and there's not enough light with the lights off here. Yeah, you probably will. No, you won't. I've got it. No, I don't, because I hit.
Negative 1.8.
I only did 1 over 0.5, which I kind of knew was 2. Equals negative 1.81 repeating meters. So that's the image distance. Notice it's negative because it's on the same side as the object. Just like we had already said, it's going to be virtual because it's on the same side. So now the question is, how far is it from her eyeball to that image? Okay, take the magnitude of this, right? It's minus because of its direction, takes magnitude. So you have far point is equal to 1.81 meters plus 0.0175 meters equals 1.8275 meters. But of course, we don't have that many sig figs. We only, using correct math, that's equal to 1.83 meters. And you know what? You don't need eyeglasses if your vision's that good. I mean, if you can see clearly out beyond a meter, you don't need eyeglasses. Basically, that's about where my far point is. I do need them a little, like at nighttime driving, maybe. But yeah, her vision here is 1.83. She really doesn't need them. Do you understand, Michael?
Yes.
All right.
Thanks.
Let us adjourn now so Trace can have a little extra time and not say, I knew it was too good to be true.
No, I did realize something.
What's that?
In lab, I expected the answer to the question I asked.